Hello everyone, welcome to my presentation. Today I'll be discussing my analysis of the abalone dataset, focusing on data preprocessing, modeling, and insights derived from the results. My goal is to provide a clear and logical explanation for the steps involved, demonstrate technical depths by discussing key models, and align with the learning objectives. Along the way, I will reference visualizations and results to support my conclusions. So the first prompt is about the data preprocessing. To prepare the abalone dataset for modeling, several preprocessing steps were followed to ensure the data was clean and suitable for analysis. First, we perform the EDA and visualizations like histogram. Revealed that the target variable rings was skewed, which necessitates transformation to improve the model's accuracy. A correlation heat map also showed strong relationships between features such as length, height, hole weight, shell weight, and these correlated features suggest that some variables might carry redundant information, a factor to consider when choosing models to minimize multicollinearity effects. Um, Then, the box plot identify outliers, particularly in the target variable. And removing these outliers using the Taki rule ensured that the data set was more representative, reducing noise that could negatively impact model performance. And scaling was another critical step, with features standardized to have a mean of 0 and standard deviation of 1. That was particularly important for models like SVR and neural networks, which are really sensitive to feature scales. Finally, the data set was split into training and testing subsets using an 80 to 20 split. And test validation ensures that the model are evaluated on unseen data, reducing the risk of overfitting. So we're done with the pre-processing, and we're going to the second prompt, the modeling in technical depths. So I will evaluate the performance and trade-offs of multiple linear regression, logistic regression, and tree-based models. So for the multiple linear regression, it serves as a baseline model for regression tasks right here. It, it assumes linear relationship between predictor and the target. In the data set, the model had the fair R-square value, indicating that the linear assumption could not really capture the complexity of the data. And the bias in the model was pretty high as it underfit the data due to its simplicity. And for logistic regression, although primarily used for classification tasks, it was adapted to analyze the binary coded sex feature. Its application here highlighted its ability to model relationships between categorical and continuous variables. However, the performance was limited due to the dataset's regression nature, making logistic regression not really suited for predicting the target variable. Thirdly, the tree-based model, which is the random forest regressor. The random forest um, here, the random forest emerged as one of the best performing models for the data set. Its ability to handle correlated features and capture nonlinear relationship made it an excellent fit. The R-square value for random forest was the highest among all the models, showing that it explained a significant portion of the variance in the target variable. The feature importance chart generated by the model revealed that length, weight were the most influential predictors, aligned with our expectations based on dataset structure. And for the bias variance trade-off, the random forest model achieved a good balance between bias and the variance, leveraging its ensemble nature to reduce overfitting while maintaining flexibility. In contrast, multiple linear regression had high bias, underfitting the data, while neural networks had a tendency toward high variance due to their complexity, requiring careful regularization. And lastly, um, the ridge regression here achieved the highest R-square value among all the models, indicating its superior ability to explain the variance in the target variables rings. Ridge regression's strength lies in its ability to handle multicollinearity among features such as length, height, and weight, which are naturally correlated in the abalone dataset. By applying L2 regularization, ridge regression penalized large coefficients, stabilizing the model and reducing overfitting. This balance between bias and variance allowed it to outperform both simpler models like standard linear regression and more complex models such as neural networks, which may have struggled with overfitting or require larger datasets. Its performance highlights the importance of using regularization when dealing with datasets that exhibit multicollinearity and noise relationships, which makes ridge regression a robust and good choice for this analysis. Thirdly, we're going to talk about the insights for the real-world applications. So visualization played a critical role in supporting all these findings. The feature importance bar chart from the random forest confirmed that measurable physical attributes like length and weight were the most significant predictors. Residual plot for random forest and SVR reviewed these revealed tightly clustered residuals, indicating strong predictive accuracy. The R-squared value for the model reinforced these observations. Random forest and ensemble model underperform others, with R-squared value close to 1. With R-squared value being the highest, close to 0.5, indicating their ability to capture most of the variability in the data. Cross-validation metrics such as mean squared error further validate these models' reliability. These insights have real-world applications. In ecological research, the ability to predict the growth or age of abalone populations can inform conservation strategies. For the seafood industry, for example, accurate predictions of weight or size can optimize harvesting practices, ensuring sustainability while maximizing yields. In conclusion, this analysis highlights the importance of thoughtful data preprocessing and evaluation of multiple regression models and the use of tree-based methods for robust predictions. By addressing skewness, removing outliers, and applying validation techniques, we ensure the model were reliable and effective. The R-squared values feature importance charts and residual plots provide strong evidence for these conclusions. This analysis demonstrates how machine learning can solve real-world challenges in ecology and industries. Thank you for watching.